this tutorial. Yeah. All right. Today I will go over the tutorial for level 5 and level 7. And then I released a Python script for the level 5 and level 8, which is the 64-bit counterpart of the level 7. So if you follow the level 5 and level 7, then you can easily extend that to the 64-bit one, level 6 and level 8. And for the level 9, you need to think about a little bit more to solve that. But I'm sure that if you follow this tutorial very well, then you can also solve a level 9 by your own. And let's start with the example for level 5. And today I will give a brief tutorial for like the how you can write the Python script to solve the challenge. So I will write a Python script for it, and then also using GDB to trace that. And you guys can follow the steps that I'm taking when you are actually exploiting the vulnerabilities in the challenge. And let's start with the reverse engineering the challenge first. So in the main function of the buffer overflow level 5, it has a run function in the middle. And disassemble of the run function, it calls puts 3 times. And now we know that the puts is just like the calling the this one as a first argument. So I will not gonna get into the details of the reverse engineering of these things. And then the important thing is like this run function calls a receive input function internally. And then inside the receive input function, it's very simple and reserve the stack local space as a like a 0x88, which is a 128 plus 8 is a 136, right? Yeah. And then this is a read function. So we have read, and then its first argument is like the last one pushed on the stack. So read 0. So it reads from the standard input. And then second argument is like it's a second end from the stack. So the EAX. So it comes from the address of the EBP minus 0x80 because it's a LEA EBP minus 0x80 to EAX. And then the last element is the push 0x84. So what it means is like we have a buffer at the EBP minus 0x80, and then we will receive up to 0x84 bytes. And then EBP minus 0x80 to EBP, this is sized 0x80 exactly. And then at the address of the EBP, we have a saved EBP stored on it. And we can definitely overwrite these 4 bytes because we have a read size up to 84. So it can overwrite up to starting from EBP minus 80 and 0x80 to EBP, and then overwrite the saved EBP, but it cannot overwrite EBP plus 4, which stores the return address. So if you just overwrite all the values, it will crash. And then let's try to watch that what will happen if we just overwrite all the values with some of the address of the getter shell, as we did in like the previous examples for the exploiting the simple buffer overflow challenges. And to do that, I will write a Pontool script. So before that, please make sure that you get into the Tmux session, because we will do side-by-side Tmux and GDB session for the editing the Python script, running the script, and also the debugging. Yeah. So to use the Pontool, you need to write a Python script. So I will write it as e.py. Yeah. And then let me move the, all right, yeah. And then use the hashbang. So we will run the Python interpreter for the running the script, and then you need to import all the things from Pontools. And then one of the setup that you can use is like the default setup of the Tmux and GDB with Pontools is quite weird. So if you write the context terminal Tmux, so we will use Tmux, and then split W, we will split the screen vertically, and then H, then it will split the terminal side by side. So that on the left side, we can see the execution, and on the right side, and then we can see the screen of the GDB if we do like this. And then to execute the program, you can create the process object with the name of the target binary. But at this point, to use debugger, so if we run this program, buffer overflow level 5, we cannot attach to the GDB in the script because, so this program located here, so it will run as a inherited GID if we run this program. So we cannot directly debug it if its privilege has been escalated to this group ID. So to debug the program, one of the tricks is that we can, because we have a read permission to the program, so we can copy this file and create another file and debug that program. And then later we can just switch the name of the file to launch the attack to the target one. So to make it simple, I will just demonstrate the example. So what we can do is like we can just copy this binary program to maybe buffer overflow level X. The reason why I use the name of the buffer overflow level X is like the file name actually matters on the how we use the stack. So I don't want to change the arrangement of the stack addresses, because exploiting this program and that program, I want to make sure that all the addresses are the same. In that case, like if we can successfully exploit the vulnerability in this program, then we can also use the same trick to exploit same address and all the same exploit vector to attack this program also. So please make sure that you have the same length of the name when you copy the binary program from the privileged one to the unprivileged one. So that's why it is just marked as a green one. And then it's owned by my user ID, and it does not have like a privilege escalation bits here. So after doing that, so instead of attaching the process to the buffer overflow level 5, we can use buffer overflow level X. And then in the pawn tools, you can attach GDB by the command gdb.attach and just apply P. And then because right now we will not do anything and then just see how it works. So let's run the p.interactive and then try to run the script. And I just run the script. Oh, yeah. What is that? I made a mistake on this. So it should be equal. Yeah. Then, so now you see the screen, the side by side. So on the right side, we can see the screen of the GDB stopped at like a receiving input. So how you can detect like where it stopped, if you see like a kernel vsyscall or something, then try to look at this backtrace part of the GDB. Then you can see that the program execution was starting from the libc start main, run, receive input, and internally it called the read function, and then internally it passed the execution to the kernel to actually get the input from the user. Yeah, so you can see that. And what we want to do is like we want to exploit, I don't know, this receive input function, and then we want to monitor like how it will execute after like we run the leave writ and then leave writ in the run function. So what we want to do is like we want to set the breakpoint at the receive input plus 32 and then trace it. when we supply some of the long input of the get a shell function in this script. And let's do that. So I will just quit GDB and then go back to the script. And first, I want to set a breakpoint as a receive input plus 32. In that case, how I can do that is I can actually supply the automatic commands that I would like to run after the attaching GDB to the target process as the second argument of this function. So just put it like this, then if you run it, it'll open the GDB and then try to continue to execute. And because it waits for the sum of the input, I can put something like this, then it will stop at exactly at the receive input plus 32. Yeah. So we can set the breakpoint, and then another thing is we can prepare some buffer, and we know the size of the buffer is the buffer is at EBP minus 0x80. So we can check that from the instruction LEA minus 0x80 EBP to EAX, and then later it pushed the EAX to the stack to pass that as a parameter for the second argument of the receive. And then to draw some of the diagram for the buffer. So this is a buffer. And then this is a EVP minus 0x80. And then we could have save the EVP here. And then this is right at the EVP. And then we will have return address here. And this is location of the EVP plus 4. Yeah. And one of the rule of the thumb of the exploiting the buffer overflow vulnerability is that the EVP plus 4 will always store the return address if the execution is not in the function prologue or epilogue, and then EVP will store the saved EVP. Yeah. And because the buffer size is 0x80, so maybe we can prepare a buffer, and then what we want to do is we want to fill all the buffer as a get a shell or something. Yeah. And to do that, we need to get the address of the getter shell. And to do that easily on the pawn tool, you can use the p.elf. Then it will get the binary object, which is in the executable linkable format. Yeah, that's why it is it's called ELF. ELF stands for the executable and linkable format, which is the format of the executable binary program here. And you can look up for the symbols, and symbols means like a function name or a variable name or something like that, and search for the getter shell. Then it will give the address of the getter shell to you. So maybe we can write it as a getter shell like this. And to check if that fetches the address correctly, we can print it out. For example, if we do something like this, then we can see that if it fetches the address of the getter shell correctly or not. And let's just run the script at this point. No. So it printed out this value, 80484CB, and then maybe we can run print get a shell. Then the address of the getter shell is 80484CB. So you can use that function and commands to fetch the address of the getter shell programmatically. Yeah. And then the next is preparing some of the buffer material. And we know that the P32 getter shell will create the string for the exact address of the address value of this one. And then we know that the buffer size is a 0x80. And another thing we know is a P32 will generate a 4-byte data. So if we do something like this, then this value will be repeated up to this amount of time, then all the buffer will be filled as a getter shell. And then maybe because we can overwrite up to this point, because we can overwrite 0x84, not 88. So we cannot overwrite this one, but we can only overwrite this one. So it's something like this. So maybe we can put BBBB as an example here. And then p.send line will send it to the program, and we can actually debug the program. And let's see what it will happen if we just fill entire buffer and the save the EBP with the value of the address of the getter shell. So I will just run e.py, and then I will continue. And because I set the breakpoint at the receive input plus 32, it will stop it right here. And let's focus on the value of the EBP and ESP. So right now, EBP points to FFFFBEA8. And then because before running the function epilogue, the EBP will store the saved EBP. And in the code, we intentionally changed the saved EBP value as a BBBB. So it successfully changed it like this. And then ESP is at here somewhere below the EBP. And maybe we can check the buffer. So for example, EBP minus 0x80 was the where the buffer is located, but maybe we can put the EBP minus 90 to see like if that is correct. So this is EBP minus 90, so which is 16 bytes below the buffer. So the buffer starts at here, and we can see that the buffer data are all filled with the getter shell, the address of the getter shell. And then this is where EBP is located. So we have a buffer at the EBP minus 80. So 10, 20, 30, 40, 50, 60, 70, 80, and then we have an EBP here. Yeah. So we can get the address of the buffer from here, and also address of the EBP at here, like this. And then we will just run the leave instruction. And what leave instruction does is it will change the ESP to the value of this one, and then pop EBP. So the value of the EBP will be 42424242, and then ESP should point to here. And then that will be BEAC. And then let's check what happens if we just do NI. So we just executed the leave instruction, and then the value of EBP has been changed to the BBBB, and then value of the ESP changed to BEAC. And then right now, what it stores is like the original return address, because we cannot change the return address of the receive input function. So it will return to the run function. Yeah. So let's do next instruction. And then this instruction, nope, no operation, so it does nothing. And this instruction exists because this code is not optimized as well, and just ignore it. And then we met another leave instruction at the upper level function, run function. And if we try to run this, then what it will do is it will first change ESP to the location pointed by EBP. So ESP will be changed to 42424242, and then try to pop EBP. So it will generate the segmentation fault, and then the fault address is 42424242, because right now the ESP has not been changed because this instruction running has not been committed. And then during the execution of the instruction, it generates the memory error at this address, because it tries to change the value of the ESP to this one, and then tries to pop something from here. And then because this is not a valid address, for example, this is not a valid address. And then if you run vmmap, then you can see that all the valid address here. And then this address is definitely not in the list over here, so it will generate the segmentation fault, and we cannot read that. Yeah, but what we know that is like in the previous example, we know the buffer address is located here, and then if we change the saved EBP to here, then it will fetch the it will do the return of the run function around this point. And then we can make the second return, this one, fetch the return address from this point if we set the saved EBP as a this value. And let's do that. So the important thing is like you need to one need to like identify the actual address of the where you control the some of the value inside that address. And then if you set that as the save the EVP, then that plus that point plus 4 should be the return address. Should have the return address to return to the to change the control flow to the target function. And let's do that. And before that, I will just copy this address. Go back to the script. So, and we have a buffer address at here. And what I will do is I will reduce the, no, maybe doing this will let us have an additional space at here. And then I will put CCCC here. Yeah. And then as a buffer address, as a saved EVP, I will put the buffer address here. Then what we just do is like we just put this buffer address at the saved EVP, and then at the start of the buffer, we put CCCC, and then the rest of the buffer are filled with the getter shell. Maybe to do it correctly, maybe we can do it something like this. Then we fill the buffer like something like it's CCCC and then get a shell, and then DDDDDDDD. And then buffer address for the saved EVP. So we fill the buffer like this, and then the buffer address will point to here. Then this point, this address plus 4 will store the address of the getter shell. And let's take a look at how the execution of the program with this input will go through. So I will run e.py, and then I will just continue. Now we stopped at the receive input plus 32. Then, so focus on the EBP and ESP. They are like the normal values. And then, so it points to the start of the buffer. So it points to where we store CCCC, right? So next instruction, it will change EBP to the where we have the buffer. And then ESP is just pointing to the original return address. So here, the weird thing is that the EBP should always have the bigger value than ESP in usual, but now ESP has the bigger value because we changed the value of the EBP to points like that. So that's the frame pointer attack. And then the first return will return to the original return address. So it will return to the run function. And then there will be second leave. And what it will do is like it will change ESP to EBP and then pop EBP. And what we have at the EBP is that, so it will pop this value as the EBP. So EBP will be CCCC, so 43434343, and then ESP will point to here, and then the following return instruction should return to this address, which is a function of the address of the getter shell. So I will just run the next instruction, ni command to run this leave instruction. Then the value of the EBP has been changed to CCCC, and ESP points to the stack where it stores the address of the getter shell. So if I just continue, then you can get a privileged shell at here. Yeah. But right now, we attack the buffer overflow level X, which we copied to debug the program. So right now, you cannot cat the flag, but how you can do is, so after having a successful exploit, what you can do is you can change the script to directly working with the buffer overflow level 5 and remove gdb.attach, because gdb.attach will fail to the if you try to attach that to the privilege escalated program. And then leave the rest of the thing as the same and try to run it. Then now you can get the GID and you can cat the flag. This is how you can exploit the buffer overflow level 5. Before moving to the buffer overflow level 7, is there any question? No questions at all? So is it all clear? So this is the exactly same thing that we have gone through on this lecture slide. And then I just demonstrated this in the GDB and then how you can write a program script for it. Yeah. Yes, that's right. Like the reason why I record this and then post it on the YouTube, because like this kind of thing requires some of the practice. And then like if you have any kind of mistake on the address value, it will never work. And then you need to go through all the debugging and then all the dirty stuff that the Intel CPU and then debugger spit out. But if you watch it again and again, and then also try to draw, yeah, the stack diagram by your own, as we have gone through the stack diagram on the slide, then like you can follow how the CPU executes with the program with your input. Yeah. Yeah. And I will go over to buffer overflow level 7 as well. So there was a fun comment that I should do cat flag at here, but you guys can do that by yourself. Yeah, I don't want to steal the moment that you can actually steal the flag from the program by your hands by like the typing cat flag here. So I will never do that. Yeah, but you can do that by your own. And let's move on to the buffer overflow level 7. And let's take a look at the program. And the program's structure are very similar with the level 5. It has a run function here, and then it has a 3 or 4 puts, and then it has a receive input. And then in the receive input function, it has a little different code. And then what it actually do is, let's try to do a little bit of reverse engineering for this one. Because understanding the C code is important for this challenge. So I can create this as .txt. Then we know that these are the function prolog. Then we have a app-gets here. Then app-gets, and then the first argument is this one. The second argument is this one. Then third argument is this one. Yeah. And then to know that what's in here is that move to the flow level 7. So this one, right? So this says like it is a variable, not here. I should check this one. So this is a standard in glibc. So what it does is, and then for this one, from the address, we can see that like the 804A something in 32-bit refers to the global variable area. And then this is a global variable named as a buffer. So we have a global variable buffer, and then we can safely assume that its size is up to this 256, which is a 0x100. And then we can change it to the buffer. Yeah. And then we can ignore the next line, and then we can reverse engineer this one too. And it has a jump instruction. It will jump to the 86, and then it will move something and compare and jump it again to the 48. So we can see some of the loop structure here. So it will jump to 86 and 48 and do it again and again. And before that, we can see that this line and try to interpret that, and then what's in there. So it says the variable I, and then it is defined as a global variable. So maybe we can think it as there's a global variable I, and then that is set as 0 because I just see, so the chat message, and then one question was, so why do we need to copy the program again just for the GDB permission? Yes, that's right. If we don't copy the program, then we cannot attach GDB in the Python script. That's why we need to copy it. And then the important thing is like we need to set the length of the name as the same. That's why I use the name of the BOF-level X to make it as have the same length with the name of this one. Yeah. So if you try to attach GDB in the Python script directly to the privileged permission binary, then it will never work. So that's why. And we just finished it, the reverse engineering up to this point. And then
what tells you that the I is a global variable?
So it has an address as a 804A 160. So if it is a local variable, then it will fetch the value from the EBP minus something. Yeah.
Okay.
So something like the EBP minus 88, 80, or EBP minus 10. These are the local variable on the stack, but it has the direct address value for that. So it has a no $sign. So it will put 0 to the point, the location pointed by this address. So direct addressing usually refers to the accessing the global variable. Yeah.
Oh, okay.
That's why.
Okay. All right.
So just to recall that the accessing of the local variable should be done by referring to the indexing over EBP. And then
So I
if
knew that
that is
EBP was a local variable. I wasn't
right,
sure how you knew it
yes,
from the direct address. Okay.
that's right. So you can regard all those kind of the direct address accessing as accessing the global variable. Yeah. And then it says it jumps to the this point, and then this is I. So move that to EAX, and then compare I to 0x88. So we can write a for loop I equals 0, and then I jump LE. and then compare this with the 0x88, and then JLE is a jump less or equal. So less or equal, then it will jump back to 48 and then run it again. Yeah. And then the right before this instruction, we can see that it will do EAX is I, then EAX plus 1, and then put EAX back to I, right? So it will be something like this. And internally, it will run these 4 lines of the instruction. Yeah. And then we will interpret it as EAX will have I, EDX will have the value of the I, and then MOV ZVL. So move 0 extension. 0 extension means that we will ignore the sign bit. So it's about like the extending 1 byte as a 4 byte, because the target register is a 4 byte, and the B means like we will read 1 byte from this one, and then L means like the target is long, so which is a 4 byte. So what it will do is like it will access this is the buffer, right? So buffer EDX, and then we know that the EDX is I here, right? And that will be stored into EDX. And then DL is the last byte of the EDX register. So you can regard this as an EDX. And then what it will do is there is a variable at the EBP minus 0x88. And then it'll be accessed with the EAX multiplied by 1. So from here, yeah. And then we know that the EAX is I. Yeah. And then that will store EDX. So to simplify this code, what it does is there's a variable EBP minus 88, which means like some of the local buffer, and then it will store buffer I, because EDX comes from buffer I here. Yeah. And then the function returns. So if we combine all the code, and remove some of the unnecessary stuff, so I will just remove all the global variables. So it's something like this. So it's quite short and simple code. What it does is like it will get your input up to 256 bytes, but what it will do is like it will copy exactly 0x89 bytes. The reason is if this kind of the equality was this, then this is 0x88 bytes. But because this includes the last index, so it will copy 0x89 bytes. And then what this means is that we have a buffer at the local variable at EBP minus 88. So this is a different buffer with the this local variable, global variable buffer. And then we have saved EBP and then return address. And we know that this is at EBP minus 0x88. Yeah. So if we put 88 bytes, then we can overwrite up to here. And then because we can write 0x89 bytes, and then we can overwrite the, if we have saved the EBP as A, B, C, D, these 4 bytes, then we can overwrite this first byte, which is the last byte of the EBP in the little endian. So we can only overwrite this byte, not the entire EBP. So please recall that in the example of the buffer overflow 5, we changed the entire saved EBP to point to our local buffer address. So that requires us to change like an entire 4 bytes of the saved EBP, but in this case, it can only overwrite 1 byte. And maybe in the previous example, you guys can think about like why programmers write the program like that to cause some of the buffer overflow vulnerability. But in this case, you can think it as a more realistic example. So in case of you define the local variable size the 0x88, but if you make a mistake of like having an equality sign at here, yeah, then it will overwrite 1 byte overflow, just having a 1 byte overflow to the saved EBP. But the challenge is asking you that in case of like the developer had this kind of the very little mistake, having a 1 equal sign in here, can you exploit this as a vulnerability and run a shell out of the program? That's what this challenge is for. Yeah. And we can definitely do that. And let's try to follow that. Let's try to do that. And to do that, I will just copy this kind of the reverse engineering result, and then write the e.py. Then we will have these lines as a comments. And then to work with that, I will just copy the buffer overflow level 7 as a buffer overflow level X to have the unprivileged binary. And then we'll make the e.py to be executable, and then get back to the terminal. And we need to do this first to use the GDB and tmux. So, and then we will attach, no, before this, we need to all tools from the Pwn tools, and then we will run buffer overflow level X. Then we can attach GDB, this one, and then what we want to do is we want to set a breakpoint at the receive input plus 99 at the leave of the receive input. So receive input plus 99. So we will set the breakpoint at there. And then run p.interactive. And let's check it runs correctly. So it runs, and then if I just do continue and supply some of the input, then it will stop at leave. Yeah. And after having this kind of debugging environment, what we will do is just having some of the buffer material. And before that, our final purpose is like that we want to run the get a shell function. So get that address first. And what we will do is maybe we can fill the buffer as we know that the buffer size is 88, 0x88. And then maybe we can put BBBB at the end. And then send that. And let's see what's happening to the program. So I just run the e.py, and then I think it will be better to show that the EBP, how EBP changes with this kind of a loop. Yeah, how the saved EBP changes with this loop. So I will set the breakpoint at the receive input plus 33 again. Which is right after the calling the fgets, which gets our input. So after sending the input to the buffer, so we get the breakpoint at here, receive input plus 33. And then at here, the value of the EBP is, I will just record the value of the EBP at here. So it was FFFFBE98. And then, so we have a buffer at the EBP minus 0x88. So these are the buffer material. And then BE98 is the EBP. So saved EBP. Let me see. So I need to copy these two. So this is EBP. And then this is saved EBP. So EBP points to here. And then the value stored the FFFFBE98 is FFFFBE88. And then we supply the 0x88 bytes of the A. So it will put like an A up to this. And then the last byte, this one, will be overwritten as a B. So that it should be 42. And I will just continue it here. And let's see. So can you see that the last byte of the saved EBP, just the last byte has been changed to this one? So if we just print out the buffer again, then it will fill 0x88 bytes. So 8 lines are 0x80, and then another 8 bytes as a value A. And then the last byte of the EBP has been changed to 42. So we can only control 1 byte, not the full 4 bytes. Yeah. So that's the condition. Yeah. So in this case, what we want to do is like we want to make this saved EBP to point somewhere in the buffer. And then if we set it as, for example, not 42, maybe 40 or 30, yeah, then we can make the saved EBP to point here. And then if this one stores the address of the getter shell, then we can control the program and run the getter shell function. But right now, let's see how it will be executing. So if we run leave, then the EBP will be changed to here, and then return. Nope. And then try to run leave. So it will point to where AAAA is stored, and then return. Then right now it will return to AAAA because our buffer stores all the AAAA. So in this case, you can easily think of like the what if we change AAAA to get a shell? Then let's try to do that first. So for example, one of the things that you can easily do is you can change this as a P32 get a shell. And let's run it. Continue. Then we are at the first leave. Then next instruction. So I put the too many bytes. So because we need to divide this by 4 because P32 is a 4-byte one. Run it. Continue. Then we are at the first leave. And then we see that the saved EBP, so where EBP, the value stored on where EBP points to, has been changed. Its last byte has been changed to the 42 because we put the B character at the end. Then it will run leave and return. Nope. And then it will run leave. Then where it will returns to. So it returns to 84FV A0 A4. So it's not the address of the getter shell function. So it's somewhat misaligned because getter shell is a 0804 A4FB. So 0804 84FB. So it's like 2-byte misaligned. And then you can actually get the exact address where you should put from the printing the this kind of the all the not here, yeah, all the buffer. So for example, to get the exact address, so how I recommend is like the at the first leave, try to print out the stack buffer and then points to any address. So right now, what it has is like the save in the saved EBP is like they will point to FFFFBE42, which is not 4042. So that's why it will start with the 84FB 0804 or something. Yeah. So that's why it has a wrong address. And then it is 2-byte misaligned. So if we change it to the this 40, in that case, it will work. So let's change the character B to 40. Yeah. So the CHR will make this number. From this number, it will change that to ASCII code character. So you can write it like this. Then it will put the 0x40 as the last byte of the EBP, saved EBP. And then it will internally points to somewhere in the middle, aligned with the 4 bytes. And then we fill all this buffer as a address of the getter shell. So it will run the shell. And let's see the result. So I will continue it. And we are at the first leap. So right now, saved EVP has been changed to the FFFFBE. Last byte is 40. And then it will point to the getter shell. So leave. And then return to the run. Then here's another leave. Then ESP will point to EBP plus 4. And then it stores the address of the getter shell. And then it will return to that point. So if I continue, then I can get the shell. But right now, I ran it with the unprivileged binary, so we do not have the permission. So, and if you successfully exploit at this point, then you can disable GDB by doing this, and then change this to overflow level 7, and then run it. Then you can get the group ID and exploit that. But there is a one caveat. So right now, we have a good condition that we can control EBP easily as the by just changing the last byte. And then I will show you that some of the more tricky case about just controlling 1 byte to exploit that. So for example, so I will have something like this. And because we want to debug the program, I will run something like this and then attach GDB, and let's try to see this. So what I did is like just change the environmental variable, which will be put on the stack before running the program. So it will change the stack address a little bit. And then in this case, right? No, this is not the case. Maybe let me push a little more value. Something like this. Yeah, right now this is the condition that we might have like difficulty in exploiting the program. So what we did is like we would like to change the save the EBP, and then what we can control is like the no, this is also the easy case of the exploiting the thing. Maybe can use it EBC like this. This is also not a good case. My mistake. Maybe 100. Yes. 18. You will see what I'm trying to do after you see the result. So see this case. No, 8 more. This is not a. Maybe we go with this example. Yeah. So the problem here is that, so we know that we can only change the last byte of the save the EBP. Yeah. No, a little bit more. Sorry about that. I got confused. 130 was the right one. Yeah. So what we can do is like we can only change the last byte of the EBP. Yeah. So that means we can change this value to be 0, but let's take a look at the buffer. So we have a buffer from here to this address. So the values that we can control are starting from 0x FFFF DC70 to up to this point, which is FFFF DCF0. 0x FFFF DCF0 is here, so up to this point will be 08. So the values that we can control are stored at here, but what we have for the saved EBP is this value. And then we can change the last byte, only the last byte. In this case, no matter how we change the last byte, we cannot, because we cannot change this byte to DD, the second byte, second last byte. So we cannot make the saved EBP to point to where our buffer is located, because our buffer is located in DC, different address. And then the restriction is that we need to make this saved EBP to point to somewhere in the middle of the buffer, but by only changing the last byte, we cannot make it happen. because the second last byte is different. So in that case, no matter how you change this, you will never get this points into this. So what you can do is, just as I do, put an environmental variable and then controlling the size of this one, just put more bytes, something like this. Then you will see that your range of the buffer, for example, will span over. Oh, it has not changed it at all. Yeah, no. So the saved EBP is at the DC40, right? No, this is weird. Let's do it again. So now we are at the leave, and then so the saved EBP is FFFFDC40, and then buffer starts at FFFFDBF0. And then if we change the last byte of the saved EBP, then we can point to somewhere middle of the here. So DC40 is actually points into here. So we can change the saved EBP to points to somewhere in the middle. Then we can successfully exploit the program. So the problem that I pointed at the last moment was like if the second last byte of the saved EBP is different from like the where we control for the buffer, that's the problematic case. But in that case, what you can do is you can put some more bytes on the environmental variable and then put that as an environmental variable, then you can successfully exploit that. And for the level 6 and level 8, these are counterparts for the 64-bit counterparts for the level 5 and level 7. So if you follow the how you can exploit the level 5 and level 7 correctly, then by just changing that to the 64-bit one. So for example, change this P32 to Fit64, and then like divided by 8 or something, and then the match the 64-bit address space or something, then you can easily solve that. Any questions about the level 7?
So when you change the last bit to 40, it doesn't matter what you change the last bit as long as that last bit is in
the buffer that you can
yeah,
control?
in the buffer, since you've made every 4 bits a shell, right?
Yes. So I just choose the 40 because it is a somewhat closer value to 42 because I just put the character B at the first place. But in case of like if you have a very limited scope of the buffer. So for example, right now we have a buffer size as a quite long, 0x88, which is 136 bytes. But if that is like just 8 byte or something, then you need to put the specific address, not just your arbitrary 40, 30, or something like that. So you need to put the specific address, and then that address plus 4 should store the return address. So basically, theoretically, if you have a buffer size 4, then you can exploit this vulnerability. But in that case, you have only like a one specific value that you need to put as a last byte of the saved EBP. So right now we have many spaces for like a storing getter shell here. So if your saved EBP points to anywhere aligned with the 4 bytes, then it will work. But there could be some restrictions if the buffer size is smaller.
Okay.
So basically, it has a one level of the interaction than the buffer overflow, explaining the basic buffer overflow vulnerability. So previously, what we need to do is just overriding all the thing with the return address, which is the address of the getter shell. Then it will jump to the getter shell function for you. But in this case, you need to understand how you control EBP, the frame pointer, and then put that into your buffer and then control the return address.
Cool, honestly.
Any other questions?
I'm sure I'll have questions later, but I'm just gonna have to, get in there myself,
Right.
start doing some stuff.
Yeah. All right. So if you have more questions, please post that on Discord or Piazza or the DM to TA or me, myself, then we will kindly help you guys. And let's conclude today's tutorial exercise at this point.
Have a nice day.
Yeah. Have a nice day and thank you for your attention. Yeah, thank you. So Philip asked about do we gonna use a Ghidra or IDA? So we will not use them for this in this class because all the binary programs are quite simple. So you can simply reverse engineer the program by hand. Yeah, and then we will not gonna cover that, but you are free to use those tools. All right, thank you.